We're going to use a new method to find the solution to these two equations simultaneously. That is, we're looking for an ordered pair x and y such that if we plug x and y into the first equation, it's true, and if we plug the same x and y into the second equation, it's also true. So we're looking for that solution, that ordered pair that makes them both true at the same time. We have a technique for doing this that is useful when we can't use the substitution method as easily. The reason we can't use the substitution method is that we don't have a coefficient of 1 for either x or y. So it's a little tougher to solve for x or solve for y and replace it or substitute it into the second equation. So we're going to use this method that takes the following process. So if we multiply the top equation by 5, so I'm just going to denote that by saying I want to multiply the top equation by 5. For some reason that's not writing. So we're going to take the top equation and multiply it by 5. And I'm going to take the bottom equation and multiply it by -3. Now what I've done is I've chosen to use multiplication to have the same number of x's in each equation. So this equation turns into, if I distribute the 5, 15x minus 25y equals 35. And if I distribute the -3 to the lower equation, I get negative 15x plus 6y, be careful with the sign, a -3 times a -2 is a positive 6, equals, and once again be careful with the sign, -3 times -1 is positive 3. A negative times a negative is a positive. So what I've accomplished is I've transformed these equations into equivalent equations. So that whatever would be a solution for the original equation is still a solution for the revised equation or the transformed equation. Now, I'm going to use the idea that I can simply come along and add these two equations. Now, the reasoning is if negative 15x plus 6y, all of this is equal to 3, then if I add 3 to the right side of the first equation, that would be balanced by adding negative 15x plus 6y to the left side of the first equation, because I'd be adding equal things. This equal sign right here says that the left side and the right side are equal. So if I add the left side to the left side of the first equation and the right side to the right side of the first equation, then I have done the same thing to both sides of the first equation. It doesn't look like it, but I have, because the second equation tells me that those two things are balanced or equal. So I've added the same thing to both sides. Now, the reason I chose these numbers to multiply by is because if you look at positive 15x and negative 15x, that leaves you, when you add these two things together, when you collect your x's, you have no x's left. We've eliminated x as a variable. This is the same thing we try to accomplish when we're substituting. So this allows us to have 0x, and then we collect our y's, minus 19y equals, and then we have 35 plus 3 is 38. And of course, if we just clean this up a little bit, we have negative 19y equals 38. Now what that is essentially saying, if we divide both sides by negative 19, what that's essentially saying is that y equals -2. You can use this exact same process to eliminate y and solve for x, or you could take this answer, since it's nice and neat, and you could take it in and stick it in, let's say, for this y, and solve for x. So let's solve for x in that regard. So that means 5x minus 2 times negative 2, sorry, that's a bad 2, equals negative 1, and we're asking the question, is this a true statement? 5x minus negative 4, so we have 5x minus negative 4 equals negative 1. So we have 5x add plus 4 equals negative 1. If we subtract 4 from both sides, we get 5x equals negative 5, and we wind up getting x equals negative 1. So we're arguing that x equals negative 1 and y equals negative 2 is an ordered pair that will work for this. Let's check in our first equation. 3, so we should be able to go up here and say 3 times negative 1. This is not showing up very well in the thing. 3 times negative 1 minus 5 times negative 2. If we sort through that, we're going to get negative 3 plus 10, which is, of course, 7. So yes, we've found an answer. It works in both equations. Alternatively, we could use these same two equations to eliminate y and solve for x. So we need to choose numbers to multiply the top and bottom equation by so that we get exactly the same result of eliminating a variable. So since there are 5 y's or negative 5 y's in the top equation, and there are 2 y's in the bottom equation, if we multiply the top equation by 2 and the bottom equation by negative 5, we will accomplish getting the same number of y's with an opposite sign in the two revised equations or transformed equations. The first equation becomes 6x minus 10y equals 14. And the second equation transforms into negative 25x plus 10y equals 5. Adding these two equations together as we did before, negative 25x. Adding these two equations as we did before, you'll notice that those will cancel, and you're going to wind up with only x's, and there will be negative 19x equals 19. Divide both sides by negative 19, and you're going to get x, of course, equaling negative 1, which is what we discovered on the first slide.